Okay, inductors work differently, but they really have a lot of similarities to a capacitor. Do you remember what they do?
They hold current.
Yep. So capacitors hold voltage. They hold charge, which is the voltage. They don't. Basically, you can say a capacitor is conservative on voltage, but they let the current be whatever it needs to be to make sure their voltage. So current can immediately change a capacitor, but the voltage takes time. It takes time to charge up and discharge. Inductors, the voltage can be whatever it needs to be, but it takes time for the current to ramp up and ramp down. So the inductor. So I'm going to replace each of these with a similar statement. Yeah. Holds current. That sounds maybe a little bit too. Maintains current. It's probably. How? So it takes time to charge. Charge is wrong. Energize. I like that. Or D, energize the magnetic field in the inductor. So capacitors have an electric field between the plates. Here's the thing about electric fields. Electric fields exist for every charge that exists everywhere. All charges produce electric field. If they're positive, they go away. Negative, they go towards it. All charges everywhere in the universe either attract each other or repel each other. That's a lot to keep track of, so we generally just go net charge, because my tabletop here is full of electrons and protons to build that up. But guess what? Total charge on it's zero. It's equal numbers. So I really don't have to worry about it unless there is an excess of electrons or excess of protons. So I have a total charge. Okay, magnetic fields are only created by moving charges. Static charges just sitting there, no magnetic field. They produce electric field, but no magnetic field. So when I'm producing this magnetic field inside those coils of an inductor, I'm inherently producing a magnetic field that wants to maintain the current. So that magnetic field is going to oppose any growth in itself, so any growth in the current. It's also going to oppose any shrinkage of current. What happens is that energy in there, if the current tries to get bigger, the energy in the magnetic field will produce an inductive current that will push back against that incoming current. It's an induced current. If the current starts to shrink, energy out of the magnetic field will be used to fuel current in the same direction to try to maintain it. That's why we like them for things called chokes in power systems, where you have it there, and if you have a big surge of current from your power source, it will help tamp it down so you don't burn something up. Or if you have a drop in current because something else gets turned on somewhere, and all of a sudden you're loaded, it will take the energy out of it and help provide current for a bit. So as long as those are momentary, that choke helps keep the current. Okay, so my inductor. If I just have a coil with a big air gap in the middle, I have an inductor. The inductors you're picking up and using typically have a little iron core down the middle, so we have coated insulated wire so it doesn't conduct against that. And that iron chunk holds a magnetic field, so it works a lot like the dielectric does inside the capacitors. It boosts the total inductance. Okay. Inductors is inductance measured in henries. If I have series inductors and parallel inductors, series inductors sum, just like resistors do. Parallel inductors They follow the 1 over rule, just like resistors do. I would make sure on your equation sheet just to know your resistance, inductance, capacitance, series, and parallel for the test. That way, you get to the test. It's really easy to remember these when you're doing homework, working on your own, or looking them up. And you get to the test, you're like, which was it? That's enough. All right, RL circuit. A lot of times they're called RL circuits, or people write L over R. Why? No instant change in current. Do I need to do series and parallel inductor circuits? I think you can find the series and parallel inductance.
Yeah.
Okay. So I'm going to skip that part. I'm going to go right to the L over R circuit. So let's build our example circuit, much like we did before. 10 volts. I'm going to make this 100 ohms in this case. This 100 millihenries. I'm initially over here, I've discharged it. Single pole, double throw, flip over there, what happens? So my time constant, tau, is L over R, which is 100 millihenries over 100 ohms. 100 over 100 is going to leave me, I believe, with 1 millisecond, right? 0.1 over 100. Yeah. So after 3 milliseconds, I will be 95% of the way to my final spot. After 5 milliseconds, I'll be 99% of the way. So let's do this thing we did before. Let's do time constants. So I'll do time here. 0, 3 milliseconds, 5 milliseconds, 1 minute. A long time. Okay, I want the voltage over the inductor, voltage over the resistor, and the current in the circuit. Which one of those can I answer? The instant I flip the switch. So time 0, I know there's kind of 2 times 0. There's time 0 before it connects and time 0 after it connects. This is when we just connected. So I have a complete circuit. So it means I need 10 volts across the combination of those. Here's how I answer this. There is no instant change in current. So the current was 0 before I closed the switch. So what's the current after I close the switch? 0. So if my current is 0, what's my voltage across the resistor? Ohm's law. 0. If there's 0 volts on the resistor, what's the voltage on the inductor?
10.
Yeah. Inductors allow instant change in voltage, but none on current. Capacitors allow instant change on current, but none on voltage. Okay, after 3 milliseconds, my current has gone to 95% of its final value. Oh, hey, let's hop down here. What's going to be its final value? Well, eventually, I'm going to end up maximum current, so I have all 10 volts there and no volts here. So if I have 10 volts over that, what's 10 over that? 0.1 amps?
Yes.
So the end up 0.1 amps. So 95% of that is 0.095 amps or 95 milliamps, which is 9.5 volts. Eventually I'll have 9.9 volts, 0.099 amps, 99 milliamps. This follows exactly that same time constant percentage progression as the RC circuit. But your time constant you get differently, L over R instead of R times C. So you have to actually keep track of which is which here, such a value. When you're multiplying, if you forget which is which, it doesn't really matter because R times C and C times R is the same. This is why we don't do, like, I don't do an RL circuit specifically in class. Is because, well, this week you're going to do something, but I don't do it the first semester because you actually end up with needing a really big inductor over a small resistor to get a time constant you can watch.
mean,
But when you have that, you have a small resistor, so you have a big current. Which means then you need a big physical inductor and a big physical resistor and a big physical power supply. So,
I mean, I think like 2 weeks ago we did one like that, and the time constant was like 5 seconds or something.
yeah.
That's capacitors.
So if I flip the switch over here, my current stays the same, right? No instant change in current, so it's already flowing that direction. That means I'm going to have sudden skip in voltage over there as it discharges, so those two voltages align. And then after 3 milliseconds, I think this is right, amps, 0.5. Also, I'm going to question myself. Yeah, 0.005, 840. All right, so after 3 milliseconds after I flip the switch down, 5 milliseconds, it's down to 0.1. After a minute, everything's green. All right, my inductors and capacitors. Now, you might notice something. What's my voltage across the inductor? So I found it across my resistor and my capacitor here in both cases by using my resistor voltage, I found my inductor voltage, and using the capacitor voltage earlier, I found my inductor voltage, or my capacitor voltage. That's okay. There is an equation you might have some homework problems that we'll hit on. Voltage across the inductor is the inductance times delta I over delta T. How fast the current's changing. Delta's always change in like mathematics. So how much current changes over time. And the current through a capacitor has a mirror image type equation, which is how fast the voltage is changing. So up here, when there's no current change, there's no voltage across the inductor. When I had the biggest current change going on, there's the biggest voltage. The voltage is not proportional to the current, it's proportional to how fast the current's changing. Over here, the current is proportional to how fast the voltage is changing. You'll have a handful of homework problems that will ask things like, find the voltage across the inductor. You know, if I have I'm gonna make this one easy. I have a 1 Henry inductor and the voltage and the current is changing at 100 milliamps per second. Then you would multiply that and go, oh, the voltage is 100 millivolts. So there's some homework problems that do things like you have two 5 millihenry inductors in parallel. The current's changing at this rate. What's the voltage? Find the total inductance. You have that one statement. It's going to be so many amps per second or milliamps per second. That's what this variable is. I know it's delta I over delta T, but it's just how fast are we changing current. Just like delta D over delta T is just change of distance over time. That's how we get speed. This is how fast the voltage is changing. You'll have some problems with capacitors like that too. For those of you doing pre-calc, you will see this written as d/dt. Calculus is a d, which because you're allowing it to change over time. We don't do any calculus in here. No calculus. But if you see it, it's the same thing. Delta I over delta T for algebra. Calculus d/dt, which is d is delta is d. So anyhow, and that's the thing. Like I said, I see a lot of people get, hold it. how do I find I and T? You don't. It's one value. It's amps per second or volts per second. And those problems will probably either have that or they'll ask for it. Okay, so that's our flyby capacitor and inductor. I did not cover anything really more than you did in the ENGR 108, but you'll do a little deeper calculations in the problem. Your lab will be a little more. Because you have more skills now.